Okay, this is a video on work energy power. This is a black bear's greatest enemy is a grizzly bear. You can read all of that. Essentially, the important part is calculate the work done by a 140 kilogram black bear climbing up a 18-meter tree. Okay, so this is essentially the force of the bear, and this is also the displacement of the bear, and so they're both up. The force of the bear is actually in the form of energy, and so basically you want to kind of not think of it in terms of force. Actually, you can think of it as how much energy the bear has expended, and so the energy that he needs to counter is gravitational energy, and so gravitational energy is delta H times mass times the gravitational field strength. Okay, and so all of the energy that the bear, all the work that he does, is essentially equal to the gravitational energy. You use the mass of the bear and you use the distance that the bear traveled in the upward direction. So it's 18 meters, and it's only in the upward direction. 18 meters times 140 kilograms, and then it is times 9.8 meters per second squared, and you get joules, which is kilogram meters squared second squared. Now compare the amount of work that you do climbing a vertical rope with the amount of work that you do climbing a stairwell that is 45 degrees incline. If both activities give you you are 6 meters higher in the end. Again, the only important part is the fact that you go up. And so in the end, the amount of work done in both cases is the same amount of work. Okay, because they have both increased by 6 meters. Okay, compare the amount of work that you do, since you are the same mass in both situations, then basically it's 6 meters times 9.8 times the mass of you, and this one is 6 meters times 9.8 times the mass of you, and so they're the same. How many times bigger, larger is an object's kinetic energy if its velocity triples? Well, you know that kinetic energy is equal to 1/2 mv squared, and essentially if you now want to figure out your new kinetic energy, and that kinetic energy is tripling, then you basically just put 3 times your velocity. And 3 times your velocity is essentially 9 times larger, so this could be converted into 1/2 mv squared times 9, because 3 squared is 9, and therefore you get your old kinetic energy 9 times larger. 9 times. It says a 50 kilogram cyclist on a 10 kilogram bicycle speeds up from 5 meters per second to 10 meters per second. What is the total kinetic energy before accelerating? Kinetic energy before accelerating is mass 1/2 mv squared. And so you use 1/2 times 60, because the cyclist and the motorcyclist together are 60 kilograms, and he speeds up, or he has an initial velocity of 5. So it's 1/2 times 60 times 5 squared. That's part A. Part B, what is the total kinetic energy after accelerating? His kinetic energy after accelerating has to do with, it's dependent on his velocity and his mass after accelerating, and so it's 1/2 60 times 10 squared. How much work is done to increase the kinetic energy of the cyclist and the bicycle? And so basically, to figure out the work done, you can figure out the change in energy is work. And basically, this is kinetic energy initial, this is kinetic energy final, and so you take kinetic energy final minus kinetic energy initial, and that's how much work is done. Because you know these numbers, by the way. You just have to calculate them. Is it more work to speed up from 0 to 5 than 5 to 10? Well, basically what you need to do here is, in part D, compare how much kinetic energy he had in this situation. So from 0 to 5, the change in energy is kinetic energy at 5, all right? Kinetic energy at 5 minus kinetic energy at 0, okay? Kinetic energy at 5 minus, because this is final, minus initial. And so you just figure out both kinetic energies using the formula. This one's going to be 0. And then to speed up from 5 to 10, you figure out essentially kinetic energy at 10 minus kinetic energy at 5. Okay? And then the question is it more work? And so this is basically the work from 0 to 5. This is the work from 5 to 10. And you just have to figure out which one is bigger. If this one is bigger, then it's more work. It turns out this one is bigger. Toboggan carrying 2 children, a total mass of 85 kilograms, reaches a maximum speed at the bottom of a hill. So you've got a hill of an unknown length so far, and then all of a sudden you've got a toboggan which has reached the bottom of it, and it's at maximum speed. Then it glides to a stop in 21 meters along a horizontal surface. Okay, then it looks like it glides to a stop in 21 meters along a horizontal surface. Coefficient of friction between the the snow and the toboggan is 0.11. That's our first given information, really. Well, one mass as well. Okay. And then also, you know that the mass of the whole system is 85. Coefficient of friction, okay. Calculate the work done by kinetic friction. Okay. And so it looks like you have friction pushing back in that direction during this whole time. And it's basically slowing the thing down. Now it's doing work. All right, and so the work done by kinetic friction is essentially the energy of friction. Sorry, thermal, my mistake, is the word we will use here. Thermal energy. And so the thermal energy that is used is going to be force of kinetic friction times UK. And so the work done by friction is thermal force, this is thermal energy, which is equal to force times UK. Remember that kinetic friction is force normal times UK. Oops, I messed this formula up, sorry. This is actually delta D. If you look at the energy thermal question, and then you can also put in cosine of 180 here as well, or you can know to make it negative at the end, and I'll explain that in just a moment. So there's UK, and then also delta D, and then remembering that the normal force on a level surface is equal to the force of gravity. And so I'll maybe go over here. And so this is equal to mass times gravity times UK times delta D. And so it's going to be negative, okay? see that? Hey guys, I'm making a video in here. If you guys want to talk outside for me.
Sure. How do you
I'm making
say?
a video right now. Can you talk outside?
Can I ask for a favor? Okay,
It's going to be on the... Thanks. Okay, use the equation for work to explain why the answer of each of the following questions is 0. Thanks. A student pushes against a large maple tree with a force of magnitude of 250 newtons. How much work does the student do on this tree? And so the basically it's 0. Why is that? Because the tree doesn't move. And remember that the work is force times displacement times the cosine of the angle between the force and the displacement. Well, in this case, it is 0 because delta D is equal to 0. And so there's your work. Now, it says a 500 kilogram meteorite is traveling through space far away from any measurable force of gravity. If it travels 100 meters per second for 100 years, how much work is done on the meteorite? It is 0 because there's no force on the meteorite. It says in the question, it is far away from any force of gravity, measurable. So if it can't be measured, it's not there, apparently. And so force equals displacement times cosine of theta. And so in this case, the cosine of theta, or sorry, the force is the culprit for making it not equal to 0. And part C is work is equal to a nurse holding a newborn 3 kilogram baby at the height of 1.2 meters above the floor carries the baby 15 meters. Okay, and so the problem here is that you've got the force of gravity working on the baby, and basically this is the baby, this is the displacement of the baby, this is the force of the nurse, this is the force of gravity. Both of these forces are actually at a 90-degree angle to the displacement, and so in either situation, cosine 90 or the force of the nurse times cosine 90, both of these are equal to 0 because the angle is 90. Okay? A student constructs a pendulum using a 1 kilogram ball attached to a 70 centimeter string. The ball is pulled back and released from point W. It makes one full swing to point Z and is shown at various heights above the table. What is the speed of the pendulum at Y? Here's Y, and basically the quickest way to figure out this is to realize that it has dropped, and I'll zoom in on this picture so it's a little easier to see. From W, it starts, and then it swings, makes a full swing at Z, and it stops again, and then again and again. And this is sort of one of the pictures here. So from W, it drops a total of, well, if it's at 50, and now it's at 40, it looks like the change in height here is equal to 10 centimeters, which I'm going to convert into 0.1 meters. Okay, and so basically all of that gravitational energy has now become kinetic energy, using the law of conservation of energy here. All gravitational energy becomes kinetic. And so essentially we have the idea of mgh, h is the change in height. It used to be 10 and now it's at 0, is 1/2 mv squared. Here's going to be the velocity that I'm going to solve for. It turns out the masses cancel. We didn't even need to know the mass of the ball. And so to figure out the velocity, it's gh times 2 square rooted. This is part A. And again, it's law of conservation of energy. Gravitational energy, it falls 10 centimeters. So all of that gravitational energy from a 10 centimeter fall becomes kinetic energy. So that's the thing, you have to put that in there. What is the kinetic energy at point? Excuse me. Excuse me. What is the kinetic energy at point 0? At point Z. At point Z is it's 0. Why? Because it stops, actually. Remember, as it says right here, it makes a full swing to point Z. At the top of its swing, it is again 0. It's velocity. So its kinetic energy is mass 1/2 times mass times 0 squared. Let's see. I guess I'll make a part 2 video and we'll carry on from here.